All right, folks. On to our last interference device. And again, the main idea is you want to create two sources that are coherent and somehow have one of them travel the distance x, this or p, one, I want to travel just to travel distance p2. The path difference between them, that's the key for the whole course pretty much. The idea of path difference started in sound, moved on to light, you're going to see it in diffraction as well, and wave, you know, with some elements of modern physics, quantum physics. The idea of the path difference is the key for creating the interference information. So if the path difference is such that this geometrical path or this optical path, now that we have optical devices you can insert in the path, this distance, again, don't, you know, it's so simple. That path 1 minus path 2, if that is equal to m lambda, we have constructive interference. If that's equal to m plus a half lambda, we have destructive interference. And somewhere in between, we can find what the you know, interference pattern looks like from that as well. So the beam splitting devices that we've used so far are double slit apparatus and thin film. And with thin films, we had to pay attention to the fact that upon reflection, sometimes we have a pi phase shift. And keep in mind that we're looking at films that are, you know, we have, you know, the beam is coming at near normal incidence. We make it like this to see what's going on inside, but really the angle of incidence is pretty much zero. Okay? So Michelson Interferometer. What you have is a laser. Right? You can have a laser here and a laser source, and that shoots out a beam. Okay? And you need to split that beam. Okay? So we have something called a beam splitter. Right? Beam splitter is a piece of glass that you can buy. Right? Get. And they come in 50-50, 70-30. What does that mean? Is that they reflect 50 and they allow 50 to go through. So the beam goes up here, right? And hits a mirror, a plane mirror up here. And the other part of the beam goes this way. So the beam goes up here and it's sent down by the mirror and continues down, and you have another part of the beam that goes this way, hits another mirror and gets reflected, and these guys go and meet down here, and you have some sort of telescope with which you can observe the interference. So this arm is D1 length, this arm is D2 length. So the beam, now you split, these are two coherent beams. Why? Because they come from the same source. You split them up and you want to observe interference. We can add something small to this in a bit, but for now, it's so simple that what is the path difference? It is one goes 2D, one goes, you know, 2D2, one goes 2D1. So delta X optical is 2D2 minus 2D1. And when that is equal to m lambda, you have constructive interference. So simple. You know, yeah, so that's that. And when you have, you know, what you do with the Michelson Interferometer is a useful device for measuring indices of refraction. So you have some sort of chamber with a gas in there, okay? And the chamber has thickness T, and the gas has index of refraction N, okay? So how does this formula get modified? This is with no gas, with no chamber, okay? No material, okay? And when you have material in there, what you end up with is the following. What is the path difference now? Well, it is 2D2. Now, okay, what happens when light goes through, remember, if you have light going through a vacuum as opposed to going through a material of index of refraction N, of thickness T, okay, this does NT, this does T, the extra distance is T into N minus 1, that's coming up again, right? So what we have now is twice that. So what we have is now the optical path, delta x2 is equal to the optical path 2d2 minus the optical path 2d1, and that guy is simply geometrical path 2d1. 2d2 though is 2 into d2 geometrical plus t into n minus 1, okay? And that's equal to m lambda for maxima. So what you end up with is the following: 2d2 minus 2d1 minus 2t into n minus 1, giving you m lambda. And you can figure out, well, by looking at the telescope, you see how many interference fringes you have, and you know the thickness of the material, you know T, thickness of the chamber. You can figure out what the index of refraction of this is going to be. Okay, so this is the Michelson Interferometer. We're going to pause and go on to the derivation of the intensity for double slit apparatus.